Have you ever wondered what happens if a ship gets damaged and starts taking on water? Will it sink or will it survive? Today, we'll explore damage stability analysis, one of the most critical safety checks in ship design. 1. What is damage stability? Damage stability is the study of a ship's ability to remain afloat and stable after tank damage or tank flooding. This happens when the ship's hull is breached due to collision, grounding, structural failure. When water enters the ship, it changes weight distribution, buoyancy, and stability. The goal of damage stability analysis is simple: ensure the ship does not capsize or sink too quickly, giving time for evacuation or recovery. 2. Purpose of damage stability analysis. So, why do we perform damage stability calculations? There are three main purposes. 1. Safety of life at sea. Passengers and crew must have enough time to escape. 2. Compliance with regulations. Ships must meet international rules such as SOLAS, safety of life at sea. 3. Design optimization. Engineers design compartments and watertight divisions to limit flooding, improve survivability. In short, it's about predicting worst-case scenarios before they happen. 3. Key concept: compartmentation. Ships are divided into watertight compartments. Why? If one compartment is damaged, water is contained, the rest of the ship stays buoyant. This is called subdivision. The more effective the subdivision, the higher the ship's chance of survival. 4. What is calculated? Damage stability analysis involves simulating different damage cases. Here are the key factors engineers calculate. 1. Flooded compartments. Which compartments are damaged and filled with water? 2. Final equilibrium condition. After flooding, the ship will settle into a new position. Draft increases, trim changes, heel angle may occur. 3. Stability. GZ curve. Engineers evaluate the ship's ability to return upright using the righting arm curve. Important criteria include maximum righting lever, range of stability area, under GZ curve 4, residual freeboard. Is there still enough deck above water? 5. Down flooding points. Critical openings like doors, ventilation, hatches. If these go underwater, flooding spreads rapidly. All these factors determine whether the ship survives or fails. 5. Two main methods. There are two main approaches used. Deterministic method assumes specific damage scenarios. Example: one or two compartments flooded. Probabilistic method uses probability of different damage cases, calculates an overall survival index, A, compared with required index, R. This is the modern standard under SOLAS. 6. Real meaning in practice. Damage stability is not just theory, it directly affects ship layout, bulkhead positions, safety systems. A well-designed ship can stay afloat even after serious damage. A poorly designed one may capsize quickly. So, next time you see a ship, remember, hidden inside its design is a complex system ensuring it can survive even the worst situations. Damage stability isn't just engineering, it's life-saving design. Thanks for watching. Subscribe for more ship engineering insights.